Hello everyone and welcome to today's presentation. I'm excited to have you here as we explore Chapter 6, which focuses on graphs and hashing. Today, we'll cover some basic terminologies, how graphs are represented, and the fundamentals of hashing. So, over the next few slides, we'll delve into these concepts to build a solid understanding. Let's get started. A graph can be defined as a collection of vertices and edges that are used to connect these vertices. Think of vertices as points or nodes, and edges as the lines or connections between them. Now, you might wonder how this relates to the broader theme of this presentation. Well, graphs are fundamental structures in many complex systems, from social networks to transportation maps. You can also imagine a graph as a cyclic tree, where the nodes, or vertices, maintain complex relationships among themselves, rather than just a simple parent-child hierarchy like in traditional trees. This flexibility allows graphs to model many real-world scenarios more accurately. So, when we talk about graphs, we're really talking about a powerful way to represent interconnected data, which will be crucial as we explore more advanced topics in later slides. Let's take a closer look at what a graph G actually represents. Essentially, it's defined as an ordered set G, V, E, where V, G, stands for the set of vertices, and E, G is the set of edges that connect these vertices. Think of the vertices as points or nodes, and the edges as the lines or connections that link them together. Now, in the specific example shown here, we have a graph G with 5 vertices, labeled A, B, C, D, and E. These are the points you'll see in the figure. The graph also contains 6 edges, which connect these vertices in various ways. For instance, there's an edge between A and B, between B and C, and so on. What's really important to grasp is that the edges illustrate the relationships or connections between the vertices. This structure is fundamental in many applications, from network design to social network analysis. As we progress, you'll see how these concepts form the building blocks for understanding more complex graph algorithms and properties. So this slide helps us visualize the basic components of a graph, the vertices and the edges that connect them, setting the stage for deeper exploration into how graphs can model real-world systems. Let's take a closer look at some fundamental graph terminology. First, we have nodes or vertices. These are the elements of a graph. Think of them as the points that are connected through edges. Edges, then, are the lines or paths that connect two vertices. They represent relationships or connections between nodes. Now, when two nodes, say U and V, are connected directly by an edge, we call these nodes neighbors or adjacent nodes. This concept of adjacency helps us understand how nodes relate to each other within the graph. Another key idea is the degree of a node. The degree is simply the number of edges connected to that particular node. If a node has no edges connected to it, we call it an isolated node. This can be important when analyzing the structure of a graph because it tells us about the connectivity of individual points within the network. All these terms, nodes, edges, adjacency, and degree, are building blocks for understanding the overall structure and behavior of graphs, which is essential as we explore more complex concepts later in this presentation. A graph can be either directed or undirected, and today we're focusing on understanding the difference between these two types. In an undirected graph, the edges don't have any associated directions. That means, if there's a connection between two vertices, say A and B, you can travel from A to B or from B to A without any restrictions. The edges simply indicate a mutual relationship or connection. In the figure above, you can see an example of an undirected graph, where the edges are not attached with any arrows or directions. This visual helps us understand that the connection is bidirectional. So, when an edge exists between vertex A and B, both vertices are accessible from each other, highlighting the key characteristic of undirected graphs. Understanding this distinction is essential as we explore different types of graphs, since the directionality impacts how we traverse and analyze the connections within a network. This concept ties into the overall theme of how graphs model relationships in various systems, whether they're social networks, transportation routes, or communication links. Let's take a closer look at what a directed graph entails. In this context, the edges, which are the connections between nodes, actually form ordered pairs. This means that each edge has a specific direction, pointing from one node to another. Think of these edges as representing a particular path that starts from a specific node, which we call the initial node, and leads to another node, known as the terminal node. The directionality is crucial because it shows the flow or sequence from the start point to the end point. In the diagram that follows, you'll see an example of a directed graph. This visual will help us better understand how these nodes and edges come together to form a network with a clear direction, which is fundamental for many applications like flowcharts, state machines, or network routing. So, recognizing the roles of initial and terminal nodes, along with the importance of the directed edges, sets the foundation for understanding how complex systems can be modeled and analyzed using directed graphs in our overall study. Let's start with the concept of a predecessor. A predecessor of a node is simply the node that comes immediately before it in a sequence or a path. For example, in this case, node 2 is a predecessor of node 1 because node 2 directly precedes node 1. This idea helps us understand the direction of relationships between nodes. Now, moving on to successors. A successor is the node that immediately comes after a given node. So here, node 1 is a successor of node 2 because it directly follows node 2. Recognizing successors helps us trace the flow or progression through a network. Next, let's talk about in-degree. The in-degree of a vertex V is the number of edges that are coming into that vertex. Think of it as how many connections are directing traffic into the node. We usually denote this as deg minus V. It's a key measure to understand how much a node is influenced or affected by other nodes. Finally, out-degree refers to the number of edges that are leaving from a vertex V. It's the count of how many connections go out from that node, and we denote it as deg plus V. Out-degree indicates how much a node is spreading or distributing information to other nodes. Connecting these points to the overall theme, understanding predecessors, successors, in-degree, and out-degree helps us analyze the structure and flow within a network. They're fundamental concepts for grasping how nodes interact and how information or influence moves through the system. Now let's take a closer look at vertex A. As you can see, it has two edges that are going outwards. These are labeled ad and ob. Because there are two edges leaving A, we say its out-degree is 2. This tells us how many connections are originating from this vertex. On the other hand, there's an edge called GA that is coming towards A. This means that vertex A is receiving an incoming connection from vertex G. Since there's only one such edge, the in-degree of A is 1. Understanding these concepts of in-degree and out-degree helps us analyze the flow of information or resources through the graph. It's fundamental because it shows us not just where connections are going, but also where they are coming from, giving a complete picture of the vertex's role in the network. This ties into our overall theme of understanding the structure and dynamics within graphs, which is crucial for many applications, from network analysis to data flow. Let's now talk about paths in a graph. A path can be thought of as a sequence of nodes that you follow in order to reach a specific terminal node, which we call V, starting from an initial node U, for example. If we consider path A, C, it consists of the segments OB and BC, showing the steps from node A to B, then B to C. Now, a closed path is a special kind of path where the initial node and the terminal node are the same. So, if V0 equals Vn, meaning we start and end at the same point, we have a closed path. This concept is important because it helps us identify cycles and loops within the graph. Speaking of cycles, a cycle is a path with a unique property. It has no repeated edges or vertices, except for the first and last vertices, which are the same. This means once you complete the cycle, you return to your starting point without retracing any steps along the way. Understanding these concepts, paths, closed paths, and cycles, is fundamental to grasping how graphs work, especially in analyzing networks, routes, or relationships within a system. They help us identify loops, redundancies, and the overall structure of the graph, which is key in many applications across computer science and network analysis. Now, let's take a look at the difference between a not-connected graph and a connected graph. A not-connected graph is one in which there are some nodes that aren't reachable from others. In contrast, a connected graph is one where, for every pair of vertices, say U and V, there exists some path connecting them. This means that in a connected graph, you can start at any node and reach any other node without having to leave the graph. It's also important to note that there are no isolated nodes in a connected graph. Every node must be connected to at least one other node, ensuring the entire graph forms a single, cohesive structure. Understanding this concept is fundamental because many algorithms rely on the graph being connected to function correctly. So, in essence, connectivity is about ensuring all parts of the graph are accessible, which is crucial for network reliability and communication. Let's take a closer look at some specific types of graphs. First, we have the complete graph. This is a special kind of graph where every node is connected to every other node. So, in a complete graph, no node is isolated or disconnected. They all have direct connections with one another. An interesting point to remember is that the number of edges in a complete graph is given by the formula n times n minus 1 divided by 2. Here, n is simply the number of nodes. This formula essentially counts all the unique pairs of nodes that are connected. Next, we move to weighted graphs. These are quite useful because they allow us to assign a specific value or data to each edge. Think of it as adding a label that indicates something like the length, cost, or capacity of that connection. The weight of an edge, which we represent as W, E, must be a positive value because it usually indicates a cost or effort to traverse that edge. This makes weighted graphs particularly important in real-world applications like shortest path problems or network optimization, where the weights help us determine the most efficient routes or solutions. Both these types of graphs, complete and weighted, are fundamental to understanding complex network structures, and they connect directly to our overall theme of analyzing and optimizing interconnected systems. All right, let's look at the concept of length in a graph. The length of a graph is essentially defined by the number of edges it contains. Think of each edge as a connection between two vertices, and the total length counts all these connections within the graph. In this specific example, the length is 8, which means there are 8 edges connecting various points. These edges are OB, BC, CD, DA, EF, FA, AC, and CE. What's important to note here is how counting these edges helps us understand the structure of the graph. The more edges, the more interconnected the graph, which can have implications for things like network flow or connectivity analysis. So, in summary, the length provides a simple yet powerful way to quantify the size or complexity of a graph by just counting its edges. This concept ties back to our overall theme of understanding graph properties and their applications. Today, I want to talk about how we represent graphs in computer memory. In graph theory, a graph representation is essentially a way to store a graph so that a computer can process it efficiently. To do this, we need 2 key things. First, the set of vertices, which are the points or nodes in the graph. Second, for each vertex, we need to know its neighbors, those vertices that are directly connected to it through an edge. If we're dealing with a weighted graph, then each edge also has a weight associated with it, representing the strength or cost of the connection. Now, when it comes to actual representations, 2 common methods are the adjacency matrix and the adjacency list. Each has its own advantages depending on the specific use case. The adjacency matrix is a 2-dimensional array where each cell indicates whether an edge exists between 2 vertices, making it easy to check connections quickly. The adjacency list, on the other hand, keeps a list of neighbors for each vertex, which can be more efficient for sparse graphs. These representations are fundamental because they allow us to store and manipulate graphs efficiently, which ties directly into the overall theme of understanding graph algorithms and their applications. By choosing the right representation, we can optimize our algorithms for speed and memory usage, which is crucial in real-world scenarios. let's take a closer look at the adjacency matrix, which is a sequential way to represent a graph. Essentially, it helps us see which nodes are connected to each other. So, think of it as a simple yes or no answer. Is there an edge between node I and node j? If yes, then in our matrix, the element at row I and column j will be a 1. If not, it will be a 0. Now, when we're dealing with weighted graphs, instead of just ones and zeros, we store the actual weight of the edge. This gives us more information about the connection, like how strong or costly that connection is. To create this representation, we construct an n by n matrix, where n is the number of nodes in our graph. This matrix is a handy way to quickly see the relationships between nodes and to perform various algorithms efficiently. It really ties into the overall theme of understanding different ways to represent and analyze graphs. All right, let's look at this slide about undirected graph representation. Here, the key idea is that each entry in the matrix tells us about the connections between vertices. Specifically, a 1 indicates there is an edge from a row vertex to a column vertex, meaning these two vertices are connected. On the other hand, a 0 means there is no edge between them. It's important to understand that in an undirected graph, these connections are bidirectional, so the matrix is symmetric. That means if there's a 1 at position, row, column, there should also be a 1 at position, column, row. This matrix form is a straightforward way to visualize and analyze the structure of an undirected graph, especially when dealing with smaller graphs. It helps us quickly identify which vertices are connected and which aren't, making it a useful tool in graph theory. Overall, this representation simplifies the concept of edges and makes it easier to perform various algorithms and operations on the graph. Let's take a closer look at this representation of a directed graph. Here, the numbers 1 and 0 are our key indicators. A 1 signifies that there's an edge from a specific row vertex to a column vertex, meaning a directed connection in that direction. Conversely, a 0 indicates that there's no edge from the row vertex to the column vertex, so no directed link exists there. This kind of matrix is a straightforward way to visualize the structure of a directed graph, making it easier to analyze how vertices are connected. Understanding this matrix helps us see the overall flow and relationships within the graph, which is essential when we're dealing with complex networks or trying to optimize certain paths. It ties back to our broader theme of graph representations and how they serve as powerful tools for solving real-world problems. Today, let's take a closer look at the undirected weighted graph representation. This is a fundamental concept in graph theory and plays a crucial role in many algorithms and real-world applications. When we talk about an undirected graph, we're referring to a structure where the connections, or edges, between nodes or vertices don't have a specific direction. In other words, if node A is connected to node B, then node B is also connected to node A, making the relationship bidirectional. Now, adding weights to these edges introduces additional information, usually representing costs, distances, or capacities. These weights are crucial because they help us quantify the relationship between nodes. For example, in a transportation network, the weight might represent the distance or travel time between two locations. Representing this kind of graph visually and mathematically is key for analysis. We often use adjacency matrices or adjacency lists to do this efficiently. The adjacency matrix is a grid where each cell indicates whether a connection exists and what its weight is. The adjacency list, on the other hand, is a list of neighbors for each node, along with the corresponding weights. This representation is essential because it underpins many algorithms, like shortest path or minimum spanning tree algorithms, which are vital for solving real-world problems. It ties back into our overall theme of understanding how to model complex systems and optimize their performance through graph structures. All right, let's talk about the advantages and disadvantages of this representation. One clear advantage is that it's much easier to implement and follow. This means that once you understand the structure, working with it becomes straightforward, which is a big plus, especially when you're trying to visualize or manipulate the graph. However, on the flip side, there are some notable disadvantages. For example, this method tends to take up a lot of space because we need to store information about all the neighbors of each vertex. And it's not just about storage. When it comes to traversing the graph, we have to visit all those neighbors to get the full picture. This process can be quite time-consuming, particularly because we often need to traverse all vertices in the graph to perform certain operations. So, while this approach is user-friendly in terms of implementation, we need to be mindful of its efficiency, especially with larger graphs. This balance between ease of use and computational cost is a key theme as we explore different ways to represent graphs. Let's talk about adjacency list as a linked representation. In this approach, for each vertex in the graph, we keep a list of its neighbors. This means that every vertex contains a list of vertices directly connected to it. To implement this, we typically use an array of vertices, where each element in the array is indexed by the vertex number. For each vertex v, that array element points to a singly linked list of its adjacent vertices. This structure is very efficient for representing sparse graphs, as it only stores edges that actually exist, making it easier to traverse and analyze the connections within the graph. Overall, the adjacency list is a powerful way to organize graph data, especially when dealing with large or complex networks. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about the advantages of using adjacency lists. One of the biggest benefits is that they save a lot of space, especially when dealing with sparse graphs. Since we only store information about existing edges, it's much more efficient compared to other representations. Another key point is flexibility. We can easily insert or delete edges because we use linked lists for each adjacency. This makes updates straightforward and efficient, which is really useful when the graph changes frequently. And importantly, this representation is quite intuitive. It clearly shows which nodes are connected to which, making it easy to follow the structure of the graph visually and conceptually. Now, shifting to the disadvantages. While adjacency lists are great for checking if two vertices are connected, this operation isn't as fast as in some other representations. It can be slower because you might need to traverse the list to find the specific connection. So, in summary, adjacency lists are space-efficient and flexible, but they trade off some speed when it comes to checking adjacency between nodes. This balance is important to consider depending on the specific needs of your application or problem. Graph traversal is a technique we use to search for a specific vertex within a graph. It's really fundamental because it helps us systematically explore all parts of the graph. Additionally, traversal isn't just about finding vertices. It also helps us determine the order in which these vertices are visited during the process. One key point to remember is that when we perform a graph traversal, we're essentially identifying the edges that will be used in the search without creating loops. This means that as we visit each vertex, we avoid revisiting nodes in a way that would cause us to get stuck in a cycle or loop. So, in essence, traversal allows us to visit all vertices in the graph efficiently and without redundancy. Now, there are two main types of traversal algorithms that we typically use: breadth-first search and depth-first search. Both have their unique approaches and use cases, and understanding these methods is crucial because they form the backbone of many graph-related algorithms. In summary, graph traversal is about exploring the vertices and edges systematically, ensuring we cover the entire graph without looping back unnecessarily, and choosing the right traversal method depending on our specific problem. This concept ties directly into the overall theme of graph algorithms and their applications in solving complex problems efficiently. Now, when we perform a DFS traversal on a graph, the final outcome is a spanning tree. This means that DFS helps us connect all the vertices in a way that covers the entire graph without creating cycles, resulting in a tree that includes all nodes. Since DFS is an edge-based technique, it focuses on exploring the edges of the graph systematically. To implement DFS, we typically use a stack data structure. The size of this stack is capped at the total number of vertices in the graph, ensuring we can handle the entire traversal efficiently. So in practice, we push vertices onto the stack as we explore them, and this process helps us keep track of where we are in the traversal. In the example shown here, A, B, D, C, E, F, the DFS process will follow a depth-first approach, diving deep into each branch before backtracking, which is ideal for exploring complex graph structures thoroughly. A spanning tree is essentially a special kind of subgraph that connects all the vertices in a graph. It's like drawing a network that reaches every point without any disconnects. The key idea here is that it does this with the asterisk minimum possible number of edges asterisk. This means we're connecting everything efficiently, avoiding unnecessary links. This concept is important because it helps us understand how to create optimal networks, whether for communication, transportation, or other systems. Throughout this presentation, you'll see how spanning trees play a crucial role in solving problems related to connectivity and efficiency in graph theory. Now, when we perform a BFS traversal of a graph, the result we get is a spanning tree. This means that from our starting vertex, we explore all reachable vertices systematically, connecting them in a way that covers the entire graph without creating any cycles. It's important to note that BFS is a vertex-based technique, meaning it focuses on visiting vertices level by level. To implement this traversal efficiently, we use a queue data structure. The size of this queue is at most equal to the total number of vertices in the graph, ensuring we can handle the entire graph without running into issues. This approach helps us understand the structure of the graph better and is fundamental in many graph algorithms. Let's walk through the steps to implement a depth-first search traversal. First, we start by defining a stack. The size of this stack should be equal to the total number of vertices in the graph, which helps us keep track of our path as we explore. Next, we select any vertex to begin our traversal. We visit this starting point and push it onto the stack. This marks our initial position and sets the stage for exploring further. Then, from the vertex at the top of the stack, we look for any one of its non-visited adjacent vertices. When we find such a vertex, we visit it and push it onto the stack. This process allows us to go deeper into the graph, exploring new nodes along the way. We continue this process, repeating the step of visiting adjacent vertices and pushing them onto the stack, until there are no new vertices to visit from the current top vertex. That means we've reached a dead end in our path. At this point, we backtrack. We do this by popping the top vertex off the stack, which takes us back to the previous vertex. Think of backtracking as retracing your steps to find new paths. We repeat these steps, visiting, pushing, backtracking, until the stack becomes empty. This indicates that we've explored all possible paths from our starting point. Finally, once the stack is empty, we produce the final spanning tree. We do this by removing any unused edges from the graph, leaving us with a clear and efficient structure that represents the traversal. This process ensures a thorough exploration of the graph, capturing its connectivity in a way that's both systematic and comprehensive. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's walk through the key steps to implement BFS traversal. First, we start by defining a queue that can hold as many elements as there are vertices in the graph. This queue is essential for managing the order of traversal. Next, we select any vertex as our starting point. We visit this vertex and then insert it into the queue. This initial step kicks off the process. Then, we look at the vertex at the front of the queue. We visit all of its adjacent vertices that haven't been visited yet and insert these new vertices into the queue. This ensures that we're exploring all reachable nodes systematically. Once we've visited all the non-visited adjacent vertices of the current front vertex, and there are no new vertices to visit from it, we remove that vertex from the queue. This step helps us move on to the next set of vertices. We repeat this process, visiting all adjacent unvisited vertices and removing vertices from the front until the queue becomes empty. That indicates we've traversed all connected parts of the graph. Finally, when the queue is empty, we produce the final spanning tree. This involves removing any unused edges from the graph, which helps us visualize the minimal structure connecting all the vertices. These steps form the core of BFS traversal, allowing us to systematically explore and analyze the graph's structure. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at how graph theory is applied in computer science. It's fundamental for understanding algorithms such as Dijkstra's, Prim's, and Kruskal's algorithms. These are key for solving problems involving networks and connections. Graphs help us define the flow of computation, giving us a way to visualize how different parts of a system interact. They are also essential for representing communication networks, like the internet or social media connections, making complex relationships easier to understand. Additionally, graphs are used in organizing data efficiently, helping us manage and retrieve information quickly. Graph transformation systems work on rule-based in-memory manipulation of graphs, enabling dynamic updates and modifications. Meanwhile, graph databases ensure that data is stored securely and can be queried reliably, supporting transaction safety and persistence. A practical example is finding the shortest path in road networks, which is fundamental for navigation systems. Think about Google Maps. Locations are represented as nodes, and roads are edges. Graph theory helps determine the quickest route between 2 points, saving time and improving travel efficiency. Graph theory also plays a vital role in network security, helping us analyze and protect communication pathways from threats. Overall, the applications of graphs are vast and integral to many technological systems we rely on every day, from navigation to security and data management. Now, let's look at how graph theory plays a crucial role in various fields. In electrical engineering, for example, it's used to design circuit connections. These connections are called topologies, which basically describe how different components are linked together in a circuit. Understanding these topologies helps in optimizing circuit performance and reliability. Moving on to sociology, graph theory helps us analyze social networks. It allows us to explore how rumors spread among people or to assess the prestige of individuals within a social group. Social network analysis software leverages graph theory principles to visualize and measure these relationships, giving us insights into social dynamics. In physics and chemistry, graph theory is instrumental in studying molecules. By representing atoms as nodes and bonds as edges, scientists can analyze molecular structures, predict properties, and understand chemical behavior more effectively. Finally, in mathematics, operational research is a key area where graph theory finds many applications. It helps solve complex optimization problems, such as routing, scheduling, and resource allocation, making processes more efficient and effective. All these examples highlight how versatile and powerful graph theory is across disciplines, tying into our overarching theme of its fundamental role in problem-solving and analysis. Let's talk about hashing. Hashing is a fundamental concept in computer science and cybersecurity. Essentially, it's a process that transforms input data into a fixed-size string of characters, which appears random. This transformation is done using a hash function. One of the key points to remember is that hash functions are designed to be fast and efficient, making them ideal for various applications. Now, an important feature of hashing is that even a tiny change in the input data will produce a completely different hash. This property is called the avalanche effect, and it's crucial for ensuring data integrity. Hashing is often used to verify that data hasn't been tampered with or corrupted. Another critical aspect is that hash functions are deterministic, meaning the same input will always produce the same output. This consistency allows us to compare hashes to confirm data authenticity. In the context of overall security, hashing plays a vital role in storing passwords securely. By hashing passwords before storing them so even if someone breaches the database, they won't see the actual passwords. So, in summary, hashing underpins many security protocols and data integrity measures, making it a cornerstone of modern cybersecurity and data management strategies. Hashing is one of the searching techniques that allows us to achieve constant time, meaning the time complexity is O(1). This is a significant advantage because it means our search operation doesn't slow down as our data grows. Now, when we look at other searching methods, like linear search and binary search, they have different time complexities. In linear search, the worst-case scenario is O(n), which means in the worst case we might have to check every element. Binary search, on the other hand, improves this to O log n, but still, it depends on the number of elements. What makes hashing so powerful is that it aims to provide a constant time, regardless of the size of the data. So, how does it do that? It uses a hash table along with a hash function. The hash function takes a key and calculates an address or index where the value can be stored or found. The core idea behind hashing is to create key-value pairs, where each key maps to a specific location in the table. When we have a key, the algorithm computes the index using the hash function, which we can write as index equals hash of the key. This way, accessing or inserting data becomes very efficient because we directly go to the calculated index. So, in summary, hashing leverages the hash function and hash table to achieve quick, constant-time searches by directly computing the position of the data based on the key. This makes it an extremely effective technique for situations where speed is crucial. This slide doesn't contain enough information. That's why we're moving to the next slide. A hash table is one of the most important data structures we use in programming. It relies on a special function called a hash function, which maps a given value with a key. This mapping allows us to access elements much faster than with other structures. Think of it like a quick lookup system. A hash table stores information, and that information is made up of two main parts, the key and the value. The key is like an identifier or a label, and the value is the actual data you want to retrieve. You can implement a hash table using an associative array, which is a data structure that pairs keys with their corresponding values. This connection between keys and values is what makes the hash table so efficient for searching and data retrieval. Overall, understanding how hash tables work is fundamental, because they underpin many of the fast data access methods we rely on in software development. So let's consider an example to make this clearer. Suppose the key we're working with is the name John, and the value we want to associate it with is his phone number. When we pass the key John into the hash function, it processes it and returns an index, like in this case, index 3. This index points to the position in the hash table where John's phone number is stored. Now, while this might sound straightforward, there's an important drawback of hash functions to keep in mind. Ideally, a hash function should assign each key a unique index, so every value has its own special spot. But in reality, especially with imperfect hash functions, we often encounter something called a collision. A collision happens when two different keys, say John and Jane, hash to the same index. This is because the hash function generates the same key for different values, leading to overlapping spots in the table. And that can create issues when we're trying to retrieve data efficiently. So, understanding these limitations helps us appreciate why designing effective hash functions is so crucial for the overall performance of a hash table. This slide doesn't contain enough information. That's why we're moving to the next slide. There are three main ways of calculating the hash function that we'll be exploring today. First, we have the division method, which is quite straightforward. It's based on dividing the key by a certain number and taking the remainder as the hash value. This method is simple, but choosing the right divisor is crucial to avoid collisions. Next, we have the multiplication method. This approach involves multiplying the key by a constant, extracting a certain part of the result, and then using that as the hash value. It tends to distribute keys more evenly, especially when the constant is carefully selected. And then there's the mid-square method. Here, we square the key and then extract the middle part of the result to use as the hash value. This method can be particularly effective when keys are similar, as it helps to disperse them more uniformly across the hash table. Additionally, we have the folding method, which involves dividing the key into parts, then folding those parts together, like adding or XORing, to produce the hash value. This technique is useful for keys of varying lengths and helps in achieving better distribution. All of these methods are essential tools in designing efficient hash functions, and understanding their differences helps us select the most appropriate one for our specific application. This is the easiest method to create a hash function. The hash function can be described as h of k equals k mod n, or h of k equals k mod n plus 1. Here, h of k is the hash value obtained by dividing the key value k by the size of the hash table n, using the remainder. It's best that n is a prime number, because that helps ensure the keys are distributed more uniformly across the table. Let's look at an example of the division method. Suppose we have k equals 1276, and our hash table size n is 10. To find the hash value, we calculate 1276 mod 10, which equals 6. So the hash value we get for that key is 6. One important point to remember is that a disadvantage of the division method is that consecutive keys tend to map to consecutive hash values in the table. This can cause performance issues, especially when dealing with large data sets or many collisions. Overall, the division method is simple and effective, but we need to be aware of its limitations and choose the table size carefully, preferably a prime number, to improve key distribution and performance. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the hash function used in the multiplication method. It's written as h, k, equals n times the fractional part of k times a here. K represents the key we're hashing, and it is any constant between 0 and 1. The core idea is that we multiply the key k by this constant a, then extract just the fractional part of the result. This fractional part is then multiplied by n, which is typically the size of our hash table, to produce the hash value. To make this clearer, let's walk through an example. Suppose our key k is 123, our table size n is 100, and we choose it as approximately 0.618033. So first, we multiply 123 by 0.618033, which gives us roughly 76.018059. Next, we take the fractional part of that, which is approximately 0.018059. We then multiply this fractional part by 100, resulting in about 1.8059. Finally, we take the integer part, which is 1, and that becomes our hash value. An important advantage of this method is its flexibility. It can work with any value of a, although some choices are considered better because they tend to produce more uniformly distributed hash values. This method is quite powerful because, unlike other approaches, it doesn't restrict us to specific constants. Instead, we can experiment with different values to optimize our hash functions. Let's talk about the mid-square method, which is a quite effective hash function. The core idea here is to take the value of the key, square it, and then extract the middle r digits to serve as the hash value. The value of r isn't fixed. It depends on the size of the hash table you're working with. For example, if your hash table has 100 locations, then R would be 2 because you need 2 digits to uniquely identify a location within that range. To make this clearer, suppose the key K is 50. When we square it, 50 times 50 equals 2500. Then we look at the middle 2 digits of 2500, which in this case are 50 itself. So the hash value for this key would be 50, mapping directly to the corresponding location in the table. This method is quite intuitive because it uses the middle digits of a squared number, which helps distribute the keys more evenly across the hash table, reducing clustering. Overall, the mid-square method is a practical and reliable approach to generating hash values, especially when you choose the right R based on your table size. Now let's talk about the folding method for hashing. The key, which we'll call K, is divided into several parts: K1, K2, all the way up to Kn. Most of these parts, except possibly the last one, have the same number of digits as the address size we need. Once we have these parts, we simply add them together. An important point here is that we ignore any carry that might result from the addition. The hash function, h of k, is essentially the sum of all these parts, k1 plus k2, and so on, up to kn. To make this clearer, let's look at some examples. For instance, if we divide the key 3205 into 2 parts, 32 and 5, adding these gives us 32 plus 50, which results in 82. Similarly, with 7148 splitting into 71 and 48, their sum is 71 plus 84, giving us 55. And for 2345, splitting into 23 and 45, the sum is 23 plus 45, which equals 68. This folding method is a straightforward way to generate a hash address, and it's especially useful because it evenly distributes keys by combining different parts of the key into a single value. It's a simple yet effective technique that aligns well with our overall goal of efficient hashing. When 2 different input values have the same index, that's when we encounter what we call a collision. Let me give you an example using the division method. Suppose our key value is 6. If we take 6 mod 10, that gives us 6. Now, if the key value is 26 and we do 26 mod 10, that also gives us 6. So in this case, both values are mapped to the same index, which is 6. This overlap is what we refer to as a collision. Collisions are an important concept because they can cause issues in how we store and retrieve data efficiently. To handle this, there are techniques like open hashing, which is also called closed addressing, and closed hashing, which is known as open addressing. These methods help us manage collisions effectively, ensuring our data remains accessible and organized. Understanding how collisions happen and how to resolve them is crucial for designing efficient hash tables, which are fundamental in many computing applications. So, recognizing the problem and knowing the strategies to address it keeps our data structures functioning smoothly. In open hashing, one of the common methods used to resolve collisions is called a chaining method. Essentially, when 2 or more keys hash to the same slot, instead of trying to find an empty space elsewhere, we keep all those colliding elements linked together in a chain. This chain is often implemented as a linked list, where each node contains the data and a reference to the next node. The beauty of this approach is that it allows the hash table to handle multiple collisions at the same index efficiently. As the table grows, the chains can also grow, but in practice, maintaining a balanced chain length is important for performance. Overall, chaining is a simple yet effective way to manage collisions, and it complements the concept of open hashing by keeping all related elements connected directly at their hash index. Let's walk through how these values are being stored in our hash table using the hash function h, k equals 2k plus 3 with a table size of 10. First, we take the value 3. Calculating its index, h3 equals 2 times 3 plus 3 mod 10, which gives us 9. So the value 3 gets stored at index 9. Next, for the value 2, h2 is 2 times 2 plus 3 mod 10, resulting in 7. That means 2 goes to index 7. Moving on to 9, h9 equals 2 times 9 plus 3 mod 10, which is 1, so 9 is stored at index 1. For the value 6h, 6 calculates to 2 times 6 plus 3 mod 10, giving us 5, so 6 is placed at index 5. Now for 11h, 11 equals 2 times 11 plus 3 mod 10, which is also 5. Here, we see a collision because index 5 is already occupied by 6. Similarly, for 13, h13 is 2 times 13 plus 3 mod 10, which results in 9. But index 9 already contains the value 3. For 7h, 7 equals 2 times 7 plus 3 mod 10, giving us 7, so 7 is stored at index 7. Lastly, for 12h, 12 calculates to 2 times 12 plus 3 mod 10, which is 7, again a collision since index 7 already has 2 and 7. This process illustrates how collisions occur in hash tables and highlights the importance of collision resolution methods. In closed hashing, when a collision occurs, we need effective techniques to find the next available slot. There are 3 main methods used to handle this situation. The first one is linear probing, where we check the very next slot sequentially until we find an empty one. It's simple and easy to implement, but it can lead to clustering, which might slow things down. The second method is quadratic probing, where instead of just moving one step at a time, we probe positions that are quadratic distances away from the original hash. This helps to reduce clustering and distributes the entries more evenly. The third technique is double hashing, which involves using a second hash function to calculate the step size. This way, the probing sequence becomes more random and less prone to clustering, making the search more efficient. These techniques are crucial for maintaining the performance of closed hashing systems, especially when dealing with high load factors. Ultimately, choosing the right collision resolution method depends on the specific needs and constraints of your application. Let's talk about linear probing, which is a specific approach within open addressing. As we're aware, each cell in the hash table holds a key-value pair. Now, when a collision occurs, meaning a new key maps to a cell already occupied, linear probing comes into play. It searches for the closest available spot by moving sequentially through the table. Essentially, starting from the position where the collision happened, it checks each subsequent cell one by one until it finds an empty cell to insert the new key. This searching process is straightforward but important to understand. It's a linear, or sequential, search that continues until an empty slot is located. The key idea here is that linear probing keeps things simple by probing linearly, which means it checks the next cell in line, then the next, and so on, until it finds a free space. This method helps handle collisions efficiently, but it's also important to consider its limitations, like clustering, which can impact performance. Overall, linear probing is a fundamental concept in open addressing, helping us understand how hash tables manage collisions in a simple, systematic way. Let's consider this example for linear probing. We have the sequence A equals 3, 2, 9, 6, 11, 13, 7, 12, with m equal to 10, and our hash function h, k equals 2k plus 3. Now, when we insert these keys, the first 4, 3, 2, 9, and 6, are stored at positions 9, 7, 1, and 5 respectively, based on the hash function. Next, we look at the key 11. Its calculated index is 5, which is already occupied by 6. Since linear probing searches for the next available slot, it checks the following cells sequentially. The nearest empty cell after index 5 is index 6, so 11 is placed there. Moving on to 13, its hash index is 9, but that position is already filled. Applying linear probing again, the next empty slot is at index 0, so 13 gets stored there. The key takeaway here is how linear probing handles collisions by searching for the nearest available spot, ensuring all keys find a place in the table. This process is crucial for maintaining efficiency in hash tables, especially when multiple keys hash to the same index. Now let's look at the next key value, which is 7. When we apply our hash function, the index associated with this key is 7. However, as you can see, the cell at index 7 is already filled. So to resolve this, we use linear probing. That means we look for the next available empty cell. In this case, the nearest empty cell is at index 8, so we add the key 7 there. Moving on, the next key is 12. Again, applying the hash function, its associated index is 7. But since index 7 is already occupied, we need to find the next available slot. Using linear probing, we check index 8, which is filled, then move to index 9, which is also filled, and finally find an empty cell at index 10. So the key 12 will be stored at index 10. This process illustrates how linear probing handles collisions by sequentially searching for the next open slot. It's a fundamental concept in open addressing hash tables, ensuring we can insert new elements even when collisions occur. Let's walk through this hash table example step by step. We have an array with some initial values, and we're using a specific hash function to determine where to store each key. The hash function here is h, k equals 2 times k plus 3, all taken modulo 10. For example, when we take the key 3, we compute h3 as 2 times 3 plus 3 mod 10, which gives us 9. So the value 3 would be stored at index 9. Similarly, for the key 2, h2 equals 2 times 2 plus 3 mod 10, which results in 7, meaning 2 is stored at index 7. Moving on to 9, h9 equals 2 times 9 plus 3 mod 10, which is 21 mod 10, giving us 1. So 9 goes into index 1. For 6, h6 becomes 2 times 6 plus 3 mod 10, equaling 15 mod 10, which is 5. Therefore, 6 is stored at index 5. Now look at 11. When we compute h11, it's 2 times 11 plus 3 mod 10, which is 25 mod 10, so also 5. Notice that this causes a collision at index 5, which is an important concept in hashing. Collisions happen when two keys hash to the same index. Similarly, for 13, h13 equals 2 times 13 plus 3 mod 10, which results in 29 mod 10, or 9. So 13 is also mapped to index 9, colliding with 3. Next, for 7, h7 is 2 times 7 plus 3 mod 10, which is 17 mod 10, so index 7 again, where the value 2 is already stored. Finally, for 12, h12 equals 2 times 12 plus 3 mod 10, which is 27 mod 10, or 7, again colliding at index 7. This example illustrates how collisions can occur with hash functions, especially when multiple keys map to the same index. Managing these collisions is a key part of designing effective hash tables. When we talk about linear probing, the searching process is quite straightforward. It's performed linearly, meaning we check each slot one by one until we find either the desired key or an empty slot. Now, in contrast, quadratic probing takes a different approach. It's an open addressing technique that uses a quadratic polynomial to determine how far to move when searching for an empty slot. The key idea here is that instead of always moving just one spot at a time, with quadratic probing, we move I² spots from the point of collision, where I is the number of attempts we've made to resolve that collision. So if it's the first attempt, we move 1², which is 1 spot. If it's the second attempt, we move 2², which is 4 spots, and so on. This method helps to reduce clustering and improves the distribution of probes, making the search process more efficient in certain scenarios. Overall, quadratic probing is a clever way to handle collisions, especially when we want to avoid the clustering issues that can sometimes happen with linear probing, all while maintaining a systematic approach to finding empty slots in our hash table. This slide doesn't contain enough information. That's why we're moving to the next slide. Double hashing is an open addressing technique, which means we resolve collisions by probing new locations rather than chaining. It's particularly useful because it helps us avoid clustering, making our hash table more efficient. When a collision occurs, that is, when the slot is already occupied, this technique kicks in by using a secondary hash of the key to determine the next position to check. Instead of just moving linearly or jumping randomly, we use a second hash function to guide us. The process involves using one hash value as an index to move forward in the table, continuing this process until we find an empty slot. The first hash function is usually straightforward, like hash one of the key equals the key modulo the table size. This gives us an initial position in the table. Now, for the second hash function, We typically use something like hash 2 of the key equals a prime number minus the key modulo that prime. The prime number is chosen to be smaller than the table size to ensure good coverage and to prevent patterns that could cause repeated collisions. By combining these two hash functions, double hashing provides a more flexible and less collision-prone way to handle insertions and lookups in our hash table. It's a key technique that enhances the overall efficiency and performance of our data structure, especially as the table gets filled. This slide doesn't contain enough information. That's why we're moving to the next slide.